So here we are going to do a video lecture on tracing recursion. Let's talk about what recursion means. As you know, recursion is a function calling the same function again, hopefully with a simpler case of the earlier function. So for example, you can say sum of n numbers is equal to n plus sum of n minus 1 numbers. So we have this recursive case. We also have the base case, which is really a simple case that is not recursive, and it can be done without solving the same problem again. So the idea of the base case is to stop the recursion from going into an infinite loop, and so the base case helps us get back to the final solution. So let's start with something really simple. Let's say that you want to find the sum of the first n numbers. So we write 1 through n. Now clearly we can find this using a loop that would give you the sum of the first n numbers, but we can also give you a recursive definition of this. So sum is going to be 0 if n is equal to 0. Otherwise it's going to be n plus the sum of n minus 1 if n is greater than 0 or greater than or equal to 1. So that's a recursive definition, and we can convert that definition into a piece of code like this. So we have our function called sum, takes the argument n, which is an integer. So we will say if n is equal to 0, then we want to return 0, which is equal to this case here, else we want to return n plus sum of n minus 1, and we end the if statement here. So the idea here is that if n is 0, so we take this mathematical definition and convert that to a piece of code, a Ruby code, and the Ruby code looks just like the mathematical definition. So now how do we trace this code? Now tracing the code means that how do we know if you take this code here, it's actually going to give you the correct answer. So let's do a tracing of the code. So we start with, let's say, sum of 4, where n is 4. Now sum of 4 goes into the function with n equals 4, n is not 0, so it's going to go into this particular code. So it says, well, I have to find n plus the sum of n minus 1. Now clearly the computer cannot find this until it knows what the sum of 3 is going to be. That's where the recursion comes in. So it says, let's go back to the same function. Now let's plug in n equals 3 at this point. That should give you 3 plus sum of n minus 1, which is 2. Now the computer still cannot solve this problem, so it needs to go into another recursive call and say this is 2 plus sum of 1, and then it still cannot solve it because still the base case hasn't reached and n equals 1. So at this point it says, well, let's compute 1 plus sum of n minus 1, which is 0. Now this function call with n as 0 would lead into the base case, which says, oh, let's return 0. Now if it returns 0, then we know that this sum now be computed. That should be 1. Now if I know that sum, then I can compute this whole sum. That should be 3. Now if I know this sum to be 3, then I can compute this whole sum. That should be 6. And if I know this to be 6, then I can compute this as the whole sum, which is going to be 10. Now what you actually see is that you have like a stack growing in this direction. So each function call create a stack and leave these numbers in the stack so it can do the computation once it reaches the the base case. So until it reaches the base case, it cannot know what the final answer is going to be. Once it reaches the base case, then it can go back and build the summation backwards. So that's the idea of recursive tracing for this simple function called sum. Now let's go into a more difficult concept, which is like reversing a list using recursion. So the idea would be that if you have a list, let's say you have list is 1, 2, 3, and then what we want to go is from that list to reverse of the list, which is going to be 3, 2, 1. Now it doesn't matter what in this list, it is a list of things in Ruby. Now the question is, can we think about reversing a list recursively? Let's think about this way. So given a list, the reverse of a list is the list itself if the list has only one element. Okay, if the list has only one element, then the reverse of the list is the list itself. Now, if the list has more than one element, let's say something like this, what you can do is you can take the first of the list, which is 3, and then append it to the tail of the list. So if you take 2, 1 and reverse it, let's say you somehow magically you reverse this 2, 1 list into 1, 2 list, and then append the first of the list to that, then it would be done. So the idea here would be something like this. Let's reverse the tail of the list. Now the tail of the list in Ruby can be given as from 1 to n-1, where n is the length of the array. Since the elements start from 0 in a list, we look at the tail list, which is going from 1 to n-1 here. So if you somehow magically reverse it, so notice that the reverse, the same function. If you can magically reverse the tail of the list, which is all the list except the first one, and then somehow take that list and append the first of the list to that list, you would get a reverse of the original list. Now how does this concept work? Let's think about this. Let's say we have this list 1, 2, 3. We want to reverse it. Now in order to reverse it, my definition would be if the list has one element, which is not the case, this list has 3 elements. So I go into this recursive definition. Note that the recursive definition, the list in the recursive definition is smaller than the list in the original definition, which is important because we have to keep going down until we get to this one element base case. So what this says is that the reverse of this list, which we call L, would be equal to a list that contains the reverse of the tail of the list, which would be 2 and 3. And then if you can append the first of that list into that, so that would be 1, and then you would find the answer to that question. But the problem is I don't know the answer to this problem. So I tried to describe that again using my recursive function. My recursive definition says if you reverse of a list, so in this case this is the list, is equal to another list, unless if the list is size 1, then that list that contains the reverse of the tail of the list. So now in this case it's a list that contains just 3. And if you take that reverse of the tail of the list and somehow append the first of the list, which is 2, and then create a list like this, you would be able to find the answer. Now the problem is now I'm not done yet. So the reverse of a list that contains one element, according to my recursive definition, would be 3. So what I get is that I have a list that contains 3 and 2, and then I append 1 to it, and I'm assuming that I would end up with a list that contains 3, 2, 1. So now let's try to convert that into a piece of code. So the code must exactly look at this and then try to convert that to a piece of code. Now here I have written the code for you. So I'm going to show you this code that's written in Ruby. So here what we have is we have a function called reverse, and it takes a list. Now if the list is null, don't do anything, just return. If the list of length is 1, return the list, which is what our recursive definition said. The list has 1 element, just return the list. Otherwise, take the tail of the list, which is equal to the sublist from 1 to length minus 1, reverse that list, and then append, that's list append. Append means add this element, the first element of the list, to the end of the list. So that's it. This is my reverse function. Now how does it work? So let's go and try to make this work. Okay. Alright, so we go back here. Alright, so let me start Ruby and load the reverse.ruby, which is this function or file there. And then I'll define a list. I'll say 1, 2, 3. So let's say list is equal to 1, 2, 3, 4. And then I say reverse this list. I get 4, 3, 2, 1. Is it always going to work? What if I have some random set of things? 4, 5, 3, and 1. So let's try to reverse that. If you reverse that, you should get 1, 3, 5, 4. There we go. So what if the list is a list of things? A, 5, B, some C here. So here's a list of things. Now can we reverse this? Let's try to do that. It actually does reverse that too. So you can see the power of recursion. Reversing a list is quite easy, recursively thinking. All we are doing is reversing the tail of the list and appending the first element of the list to the tail. And then we have a base case where the list.length is 1. In that case, we return the list. So let's move on to the next topic here about recursion. So that topic is that recursion and binary trees. Now binary trees are great structure for recursion. That's because when you think about binary trees, they are defined recursively. You have a tree, you have a key node, and a left subtree and a right subtree. So when you take the entire tree, the tree itself is recursive. That means a big tree is defined using smaller trees left and right. So one of the questions we have is, how do we traverse a binary tree? Recursive. Now we can traverse a list very easily. If you have a list of things, traversing a list means we just go sequentially 1, 2, 3, 4. But if you have a binary tree like this, 1, 2, 3, 4, 5, 6, maybe 7 here, maybe 8 here, something like that, then how do we traverse this tree? So this means that we need to have some order to traverse the tree. So I'm going to introduce few orders to traverse the tree. So one order of traversal would be called preorder traversal. Let's call this preorder traversal. Now in the preorder traversal is a recursive traversal algorithm, where what you do is in the preorder traversal is you process the root first, and then the left subtree, and then the right subtree. So you have to do this recursively. Now let's see how this works. So if you start with this tree here, let's start with a very simple one first. So let's start with 1, 2, 3. So the traversal will generate 1, and then 2, and then 3. Let's go into a different tree. So you have 1, 2, 3, 4. How do we traverse this tree? Well, this would generate 1 because you are supposed to go to root first. And then once you go to the root, then you have to go to the left subtree. Now there also you process the root, and then you process the left, then you process the right. So we get 1, 2, 4, 3. What about this one here? The pre-order traversal here would be, we go to the root, and then we have to process the entire left subtree. Within that we go to the root, and then we go to the left subtree again of that. There we process the root. Once you process the root, then you process the left child of that root and the right child. Once you're done with this entire tree, you process 5. Now what this means is that we have processed the entire left tree here. Now we go into the right tree. We again follow the same order. We process the root, then we process the left child. So here is the sequence that's generated from this traversal algorithm. Now the question is, so it's called the pre-order traversal. Pre-order traversal means that process root, and then left subtree, then right subtree, and these are recursive methods. Recursive here, recursive here. Okay, how about the code? So let's write a code called preorder. So preorder traversal would be, now you have to give me a tree to traverse that. Now if you recall how we represent trees in Ruby, is that we put the left subtree as the tree of 0. Okay, so this would be the tree of 0. Then we put the key here, and then we put the right subtree as the tree of 2. So this would be tree of 1. Okay, so now we know what the left subtree is, which is the tree itself, and right subtree is the tree itself, which means it's an array of 3 elements. So let's do the preorder traversal here. Now if the tree is null, that means it's an empty tree, then do nothing, just return. Okay, else the tree is not null, so therefore we have to, according to our preorder traversal, we must process the root. So we can just say print tree of 1, which is the root, and then we have to process the left subtree, and then we have to process the right subtree. What that means is that we call preorder on the left subtree, tree of 0, and then we call the preorder on the right subtree, which is going to be tree of 2, and this is the end. So now what we have is a function that will process the root, in this case we print it, and then call the function recursively on the left subtree and call the function recursively on the right subtree. And the preorder tree, if the tree is nil, then return. Let's see how this works. So let's say that we have a tree like this. So nil 1 nil, so this is your left subtree, and here's your root, and here's your right subtree. So if you apply the function preorder to this, so what's going to happen is it's going to come and say tree is not nil because you got 3 elements here. It's going to print the tree of 1, so it's going to print 2, which is the tree of 1. And then it's going to call preorder of tree 0. Tree 0 would be this tree here, nil and 1 and nil. And then it calls the preorder of tree of 2, which in this case would be nil, 3, and nil. So these two are going to generate recursive calls. Notice that this function will be called first. So it calls the function first and it says, okay, preorder nil1 nil means print the tree 1. So print 1 and then call the preorder, let me call it preorder of the left subtree, which is nil, and then call the preorder right subtree, which is also, okay, let's go back here. Okay. All right, so we are now right here trying to process this. So we are doing this piece related to this recursive call. Now preorder nil just return. Preorder nil just return. It doesn't really do anything because if tree is nil, just return. Now, so that's for that. And what about this function call here? It would behave very similar to the function call we just did. So this should really print only the 3 and then return nil for the subtrees. So you will have return and return. So the way the numbers are going to be printed would be 2 and 1 and 3 in that order. So the tree we have is 2. According to this representation, the tree would be 2, 1, and 3. And then we see that preorder traversal gives you that 2, 1, and 3. So this concludes the short tutorial on recursion and tracing.